Sabo and my supervisor Sebastian Erdweg. Computations become more and more complex these days, and running such computations can take a very long time. However, the input of the computations often change only very marginally for a second run, which results in small changes of the output. And here comes incremental computing into play. Instead of rerunning the computation, incremental computing processes the change of the input and updates the output. And this processing of the change of the input can often only take a fraction of the time it would require to rerun the whole computation from scratch. Examples for incremental computations are incremental parsers, incremental program analysis, and incremental build systems. These computations follow the principle of inertia, meaning that a small change of the input of the program results in a small change of the output of the program. To illustrate the principle of inertia, let's have a look at parsing a program. On the left-hand side we have a Java program, on the right-hand side we have the constructed AST. What if we change the class name from app to app1? Well, the syntax node that contained the class name changes, but everything else remains the same. What about changing the return type of the method run from void to int? Again, only the syntax node containing the return type of the method will change. Or what if we introduce a new statement into the body of the while loop? The constructed AST now contains a new subtree that represents the statement, but everything else remains the same. So, small changes of the source program result in small changes of the constructed AST. So, parsing follows the principle of inertia. In this talk, I would focus on incremental computations using Datalog. And Datalog is a logic programming language that was designed as a query language. Datalog has a least fixed point semantics, but more importantly, Datalog has an incremental execution model. A Datalog program consists of a set of rules, where each rule has a rule head and a rule body. And a rule forms a logical implication, meaning that a rule body implies the rule head. And these rules here in particular, they derive the paths between nodes in a directed graph. The inputs and outputs of Datalog are relations. And because we are interested in incremental Datalog solvers, the incremental user interaction of relations are insertions and deletions of facts. Datalog processes relations of atomic data. The incremental processing of Datalog has been explored since the 80s and has been the focus of Inca. However, many computations operate on structured data. To support using Datalog on structured data, we need to encode data as input relations for the Datalog solver to understand. To enable efficient processing of these changes, we need to design the encoding in such a way that small changes of the structured data translate to small changes of the input relations. I will showcase how an encoding affects the translation of changes. We encode the source program we've seen earlier with the naive encoding and consider the same changes we've already seen. The first change updates the class name from app to app1. And this means in the relational encoding, we now to delete every fact that depended on the class name. Because here we decided to use the class name as a part of the unique identifiers, we need to delete every fact. And this is a problem, because a small change of the source program resulted in a huge change of the relational encoding. And to avoid this, we identified a design principle, where we only want to use context-insensitive unique identifiers. The second change changed the return type of the method run from void to int. In the relational encoding, this means we need to delete the fact about the method signature, but we also lose information about the argument types and the enclosing class or the method name. So even though the return type only changed, we delete every information about the method signature, and this is not desired. To circumvent this, we identified another design principle, where we only want to use unary and binary relations to keep these changes local. And at last, we introduced a new statement in the while body. And this means we need to delete every fact in the statement relation that is part of the while body, because we used indices as part of the unique identifiers, and that means we need to update these indices. And so a small change resulted in a big change of the relational encoding. To circumvent this, we introduced a new design principle that we only want to use relative positioning for list elements to avoid this. In this talk, I will present you how to encode structured data as relations that allow for efficient incremental updates of the Datalog solver. In particular, I will show how to encode structured data such as tree-shaped data and list data, and the encoding follows the design principles I introduced on the previous slide. First, let's have a look at tree-shaped data. We use a family of node relations to store the unique identifiers of the tree nodes, and this family is indexed by the node types. Additionally, we use a family of link relations to store all parent-child connections. And this family is indexed by the parent node type and the field which connects the two elements. Here we have an example tree, and we follow the first design principle by attaching each node tree a context-insensitive unique identifier. And based on these unique identifiers, we can now describe the node relations, one for the addition node type, one for the number node type. And we can describe the link relations with them, one for the left-hand side child of the addition, one for the right-hand side child of the addition, and one for the value of the number node. And here we see that we also follow the second design principle, that we only use unary and binary relations. But what happens if we change this tree by negating the right-hand side child? We now need to adapt the input encoding as well. We have a new node relation for the negation nodes, and we have a new link relation tuple that connects the negation with its child. But also we need to delete the tuple that connected the addition node with the right-hand side number node, which was with ID 3, and now reconnected with the addition node with the negation node. And you see a small change of the structured data resulted in a small change of the link relations, because everything that had to do with the value connections and the left-hand side child did not change at all. And we can use these node relations and link relations to describe Datalog programs. For example, here we use 3 rules to describe the nums relation, which collects all the number values that occur in a tree. And we use the node relations and the link relations. Now let's set our focus on list data. Instead of encoding list elements using absolute positions, we follow a design principle and use relative positioning. And to do this, we describe lists as linked lists by describing 2 relations, the first and the next relation, where the first relation connects the list node with the first element of the list, and the next relation connects a list element with its successor element. Here we have an example of a tree that represents a function call that takes 3 arguments. And in red, we highlight the links between these nodes viewed from a linked list perspective. We can use this to describe the first and next relations. But what happens if we delete, for example, the first element? Well, we need to change the first and next relations. First, we have to delete the tuple that connected the list node with the first element, which was the number node with ID 3, and insert a new tuple that connects the list node with the number node that has ID 4. But we also need to delete the next link that connected the number with ID 3 and 4. But the next link between 4 and 5 stay intact because we used relative positioning. So what have we achieved so far? We can encode structured data, such as tree-shaped data and list data, with input relations so that a Datalog solver can understand them. And this encoding enables efficient incremental updating for the incremental Datalog solvers by allowing that small changes of the structured data translate to small changes of the input relations. But how can an incremental Datalog solver now efficiently query these relational encodings? And to answer this question, we need to understand what the interactions of a Datalog solver with the relational encoding are. Well, first, an incremental Datalog solver enumerates the tuples of an input relation. It checks whether a tuple is already stored in an input relation, and it reacts to insertions and deletions. And based on these interactions, we need to exploit invariance of the encoding to answer these efficiently. In particular, we need to exploit invariance of the node relations and the link relations. Let's have a look at node relations first. Nodes have all have identifiers. But because these identifiers are unique, each node relation contains a single identifier at most once. And that means we can use sets to represent these relations. And this enables us that we have constant enumeration of elements and constant containment checks. For link relations, we first have to distinguish between link relations that connect nodes with other nodes. We call these node-to-node link relations, and link relations that connect nodes with values. And we call these node-to-value link relations. For node-to-node link relations, we have a one-to-one mapping between the parent and the child because we represented a tree with this structure. And for node-to-value link relations, we have a one-to-n mapping because the parent is always unique and has a single child over this link. But because values are not unique, a value can appear multiple times in the tree and therefore it can have multiple parents. Therefore, we have a one-to-n mapping. And based on these observations, we can enable efficient forward and backward queries using different mapping structures. The relational encoding of structured data has been present in the incremental static analysis framework INCA since 2016. The encoding enables efficient incremental speedups of up to 10,000x. We did not provide any new evaluations in this paper, but we highlight already published evaluations that used encodings of the structured data. And these papers were published at top-level venues such as PLDI, UPSLA, and ASE. In the paper, we also describe the architecture of the INCA framework. And INCA provides two front ends that compile down to Datalog, which serves as an intermediate representation. And the intermediate representation program will then be used to generate a computation network that represents the incremental Datalog solver. The computation network will then react to changes of the input and reads the input relations and updates the output relations accordingly. In the paper, we also describe how to support optional data, how we implemented the indexing structures that exploit these invariants, how to translate tree diff patches to changes of the input relations, and we talk a bit about the historical evolution of the INCA framework. To conclude, we encode structured data as relations to support incremental execution using Datalog solvers. The encoding is designed in such a way that small changes of the structured data translate to small changes of the relational encoding, and the encoding is guided by 3 design principles that we identified in the paper. We exploit invariants of the encoding such that queries of an incremental Datalog solver can be efficiently answered. We integrated this relational encoding in the Inca framework, and it is available online. Thank you for your attention.